In this video, we'll start a discussion about constant coefficient linear system differential equations and how we can use some linear algebra techniques to try to solve them. So the most general system differential equations, or in this moment, we'll look at two component systems just for making things a little bit simpler. The most general version looks like two functions, dx dt is some function f of x, y, and t, and dy dt is some function g of the same variables. Now, if we want to use linear algebra, we need to be a little more specific about the types of systems that we're looking at to be able to approach them and solve them this way. And we first off need linear systems, and we need constant coefficient systems. And what that means is that the only way that this x, y, and t can show up in these functions f and g is in the following form. Dx dt is some number a times x plus number b times y plus some function f1 of t. And dy dt is cx plus dy plus some function f2 of t. Which means if I want to write this in matrix vector form, I get that the derivative of my vector x, which will be vector x is the function x and the function y stacked on top of each other, is going to be the matrix a, b, c, d times the vector x, and then plus this vector f1 of t, f2 of t. Now if this last part here is 0, that means it's a homogeneous equation. And that's where we're going to start with this analysis here. We'll eventually get into solving non-homogeneous versions, but at the start we'll be solving the homogeneous case here. So in that homogeneous case, we're looking at something of the form vector x prime equals a matrix A times our vector x that we're trying to solve. Now, if it's homogeneous, there's no extra term on the end. This is also an autonomous equation, or an autonomous system in the case where I have more than one unknown function. Now, we've seen autonomous equations before, so we can try to use the same sorts of methods to analyze them. And I think we looked at there with equilibrium solutions, and then which way a solution moved between these solutions. So let's start by looking at equilibrium solutions, which means I want locations or values for the vector x where the derivative is 0. So we want x prime to be 0, which means I need a times the vector x to be 0. And a here is a constant matrix here. Now in linear algebra, we look at this a lot. And in general, for these problems, we'll assume the matrix A is invertible or has determinant non-zero, which means that our only solution here is the vector 0. So I have exactly one equilibrium solution, and it's the origin. Which is great, that's nice to know, but it's not really that much information to go off of in terms of how this solution's behaving. So that's, good, but what else can we do that's going to give us more info into how this is behaving? And the answer there is to look at what are called straight line solutions. And the idea is I want to know what solutions are going to go towards the equilibrium solution at 0 and which are going to go away from it. So I want to find solutions that will go directly towards or directly away from this equilibrium solution at 0. We had this idea before for autonomous equations where it was just what's going towards or away from these equilibrium solutions, but I'm going to do the same thing here. But what does this mean if we're looking in a multidimensional space? Right, up or down was all we had for our equations. What about for these systems? Now for these systems, I want to know when a solution goes directly towards or away from 0. So say I'm at a point out here. That's my value. I want to be moving either towards or away from 0. What does that mean? Well, that means that my direction vector, or my rate of change, must point either right back to the origin or right away from it, namely on this line, which is I think of my point here as a vector. It points from the origin to that point right along that same line. So for the solution to go directly towards or away from the origin, I need the velocity or the rate of change to be in the same direction up to maybe a sign change of the point itself. So I need that the derivative of v, or how v is changing, should equal some multiple for some value lambda of the vector itself. Now if I want to work this into my actual solutions for the problem, this means I need my solution derivative x prime to equal lambda times the vector x. What do I know about x prime? This is defined as the matrix A times x, which means to find these solutions, I need a vector x so that A times x equals lambda times x. And this we've seen before. These are the eigenvalues of the matrix A. So eigenvalues are important for getting these special solutions that are going to go directly towards or directly away from the origin. Let's approach this from a different angle. If I have a linear equation, just something like y prime equals a times y, I know what this answer is, right? The solution here is just y is e to the at times some constant c in front. So what happens if I take my system here, x prime equals a times x, and I try to plug in something like the solution that we had for the linear equations. So I can plug in x to equal some vector v times e to the lambda t for some choice of vector v and number lambda. What happens if I plug this in? Well, in that case, x prime is just lambda times v e to the lambda t. And then my differential equation tells me that lambda v e to the lambda t equals a times v e to the lambda t, or we're dividing up e to the lambda t, a times a vector v equals lambda times v, and we are again back to the eigenvalues of this matrix and corresponding eigenvectors that are going to give rise to solutions of this form here. So to summarize all of this, the idea that we're building towards here is the following. If we have a system of the form x prime equals a times x, where a is some constant matrix, then we can get a straight line solution of the form x of t equals v times e to the lambda t, where lambda is an eigenvalue of a with corresponding eigenvector v. So that's a start to an approach to how we can solve these systems. As long as it's constant coefficient matrix, I can find the eigenvalues, eigenvectors. We know how to do that. And from that, I can build these solutions. Now the questions then become, are these real valued? Do they actually work? And can I use this to build a general solution? All of those are really important questions to ask about this sort of setup, and it's going to depend a lot on what the eigenvalues are and how they behave, whether or not that works. But this is a start. It gives us a way to get at least some solution to these problems, and hopefully it's enough to find a general solution, solve initial value problems, all the things we want to do for differential equation systems. We can build up from this basis to do so.